Okay, I want to talk to you a little bit about momentum here today. Um, Two aspects of momentum. Well, let's back up here a minute. Some tools here. Here we get a pen here, okay? Conservation of momentum, number 1, and impulse momentum theorem, number 2. Let's slide ahead here. Now, you should be looking in your textbook anyway and reading this in the chapter, but I'll just sort of summarize things. The impulse momentum theorem is a rearrangement of Newton's second law in the form of an expression for the force applied to an object for a time duration delta t. That's called the impulse. Okay. So the product F delta t is the impulse. And P minus P0, well, that's the change in momentum. So that's why this is referred to as the impulse momentum theorem. Basically, it's another cause and effect equation. Now, there are a couple of cases that we can look at here. First case is, what if there's no external force? Okay, what if F equals 0, right? If F equals 0, then the left-hand side of this is 0, so it just says that the momentum P equals the original momentum P0. In other words, the final momentum equals the original momentum. In the case we're talking about primarily an interaction, perhaps two objects colliding together, so that the momentum before and after the interaction is the same. That's a conservation principle. We look for these conservation principles because they tell us about the rules that govern our universe. Now, the other case is if F is not equal to 0, right? Mathematically, we'd write F is not 0, okay? In which case, the impulse momentum theorem still has the impulse on the left-hand side, and that impulse is because there's some external force acting on the mass m, originally moving at velocity v0, which will change its velocity to another velocity. So you can think of that as in the case of a tennis racket hitting a tennis ball, a golf club hitting a golf ball. Any sports analogy you can think of, an external force acting on the mass to accelerate it, changing its momentum. So let's take a look at an impulse momentum problem on number 9 in your homework. Notice we have a tennis ball, okay, 60-gram tennis ball, and it's moving at 10 meters per second. Right? Okay, so that's our V0. I think I'll draw it like this. Initially, let's say the ball is moving to the left. Okay. Velocity V0 and mass M. It's going to be acted upon by a force in this direction, right? F, which acts for a certain amount of time, right? Delta T. And as a result of that impulse, the after picture is that the mass is moving in the opposite direction with the speed of 9 meters per second. Okay? Let's put the 10 up here. Okay. What is the change in momentum? Okay? So delta P. What is delta P? Delta P is defined as your final minus your original. We want to be a little careful here. These are vector quantities. So I probably thought we were done with vectors, but we're not. So the final momentum is the mass of the ball times the final velocity. And I've drawn the final velocity as being to the right. So we have the mass of 0.06 times 9. Okay. Minus the original momentum. And the original momentum is the mass of 0.06 m. And what's the original velocity? Well, it's minus 10, isn't it? Because it's pointing to the left. So we actually, that minus sign there and that one there cancel each other out and give us a positive. So we get 0.6 and 0.54. So we get a change in momentum of what, 1.14 kilograms times meters over seconds. That's our delta P. So what is the impulse in this case? What is the product F delta T equal to? Well, think about it. Okay, now here we have when collisions occur between objects, only forces present are those contact forces between the objects. Think about it this way. Here we have a ball here and a ball here, and they're moving toward each other. Okay. Okay. There's nothing, no outside forces involved. So when they strike, let's have a different color. When they strike, ball 1 will exert a force on ball 2, if this is 1 and this is 2. But ball 2 will exert a force on ball 1 in the opposite direction, equal and opposite. Looks like this. It says the force that 1 exerts on 2 is equal but opposite to the force, these are force vectors, that the force 2 exerts on 1. So that the sum of the two forces equals 0. That's what it means. These are contact forces. These are normal forces, aren't they? These are forces acting between the objects due to their surface contact. Okay, so they're normal forces. Okay. So that's what we mean up here when we talk about. Can't find it. Talk about forces acting between objects. Okay. And no external force present, only internal forces. Now, our collisions can be described then as conserving momentum, and there are 3 types of collisions that we can talk about: elastic, inelastic, and partially elastic. Elastic is an ideal case. An elastic collision, momentum is always conserved, but kinetic energy is a very special case in which kinetic energy is conserved. So if we set up the conservation momentum principle between the two objects colliding using the above formula, and also we set up a conservation of kinetic energy principle, we can derive 2 equations that relate the initial speed, v10 and v20, okay, to the outgoing speeds, v1 final. I'm sorry, that's v2, isn't it? v2 final and v1 final. So that's what these two equations are stating up here, that this is how fast particle 1 is leaving the collision site, this is how fast particle 2 is leaving the collision site, based on the masses of 1 and 2 and their initial velocities v1, 0, and v20. Okay, so let's put this to practice and look at a problem like 19. We have here two objects, so let's say M1 is 2 grams, M2 is 1 gram, V1 is 8, and V2 is, make that V10, okay. V20 is easy. V20 is 0. Right? So if you go back to the previous page, or go ahead and look it up in your book, when you have one of the particles at rest, it really simplifies the two equations that we had on the previous page. Let's see. If we go back to these two equations right here that I've circled, okay, these ones right here, notice that V20 is right here on the end of both those equations. It's going to kill both of those terms. We're only going to have the first two terms. So let's take a look at V1F. V1F, the speed of V1 is the difference between the two masses over the sum of the two masses times the original velocity. Okay, well, that's going to be 2 minus 1 over 2 plus 1 times 8. Right? Looks like 8/3 meters per second. I didn't really care about the units on the mass because we had grams on top and grams on the bottom, so that canceled each other out. So we're pretty good there. Okay, so doing elastic problems, collisions, is real easy. You just apply those two formulas that were derived from conservation of momentum and conservation of kinetic energy. An inelastic collision is known as a sticky collision, in which two objects stick together, kind of like a capture. Momentum is conserved. It's always conserved, okay, whether it's elastic or inelastic or partially elastic. But kinetic energy is not conserved. Okay. Here's an example, page number 5. Example where we have a pitching machine. So if we represent our pitching machine here, and it's got our ball inside here, right? A little ball and a big machine. Oops. It's not supposed to be a W, it's supposed to be an M. Okay. Now, why is this inelastic? Well, if you thought about it in reverse order, and you said if the before was the ball coming toward, ball merging with the machine, right? That would be an inelastic collision, the ball coming in and and hitting the machine and attaching to it. So it's kind of like a reverse inelastic, isn't it? So the machine shoots the ball out. It's a velocity v0, and the ball has a mass m. The machine is resting on a frictionless surface, so it will recoil with a velocity v and mass m, And so if we start from the standpoint that our original momentum of our combined objects is 0, because they're not moving, right? The machine and the ball together are not moving, so that means that the final momentum must also be 0. But the final momentum is comprised of two moving objects. The ball moving off with velocity v0 and the machine moving off with velocity capital V. So we've got some numbers up here. We've got the mass of our machine and the mass of our ball and the speed that the ball leaves the machine with. I think you can take that from there. Okay, sometimes we have a graphical representation of our impulse momentum theorem, and when that's the case, we can determine the impulse, which is the product of the force times the time. If we have a graph of that, we can determine the impulse. So let's draw ourselves a graph here. Got a pen here? Where's my pen? There it is. My lines are not great, but here's a graph. If we can graph force versus time. Okay. So let's imagine we turn a force on and then we turn it off. Okay. So the force is 2 newtons and it's on for 4 seconds. Okay. And we have units of seconds here and newtons on our y-axis. Okay. Well, then the color, the region underneath that graph, maybe I should use a highlighter, huh? Something. I didn't mean to use yellow, but anyway, there you go. If we shade that in, that represents the area equals the force F times delta T, right? Because we're going from, in this case, 0 to 4 seconds, so that's a change in time. Okay, so that's a nice visual representation that the area is our impulse. Okay. If we've got a graph, all right, well, let's do a problem. Let's see, where's my, there it is. What is the impulse, what is the maximum force? What is the maximum force for the following? I need to go over here and, I believe this is problem 18. Yeah, it's 18. Okay, 18 looks like this. Try to draw this graph. Okay. Let's get a new color here. Okay. It says at these are in milliseconds, a thousandth of a second. And over here we have kilonewtons of force. So our force turns on. Okay. Instantaneously turns on, and then it ramps up to another value here, which we're going to call this top value, F max. Okay. Obviously that would mean this is 2/3 F max, and this would be 1/3 F max. Now it does that ramping up in, looks like right down here, the time, I'm going to call that 2.5 seconds. Okay, so from 1 to 2.5 it ramps up. And then it comes down, let me see if I can draw this very well. It comes down and turns off at 4 seconds. Okay. Alright, let's get another color here. Now we need to figure out the area of this rather odd looking thing. Well, think about it. We've got a triangle here, which we know the base, and we've got another triangle right here, and we've got a rectangle. Now our goal is to find the maximum force, so we're looking for F max. Okay. We'll just find the area, and you have to keep the symbol F max in there for each of the different areas, and then we already know from the wording here that we have a mass and a velocity, so we can do our delta P, right? So we're gonna know what the right hand side of the equation is, and the impulse on this side, okay, will just be the area, and within that area, those three areas, you'll have F max as one of the unknowns. So your unknown will be over here on the left hand side with, you know, whatever factors involved in calculating the area of a rectangle and two triangles. On the left hand side you'll have a numerical value based on the mass and the velocity. Okay? Okay, I hope that helps give you some hints as to how to attack these three kinds of problems: impulse, momentum, conservation of momentum, as well as graphical representation of impulse.